Okay, good morning. So last class, we saw basically um, FAR filter, IAR filter, and their stability. Um, what is basically an FAR filter? Why do you call it FAR filter? Why do you call it a finite impulse response? And why do you call the other one infinite impulse response? And are they stable always, or when will they be stable? Those conditions we have seen. So today we shall see the properties of DFT. We have already studied properties of Fourier transform, set transform, etc. So we shall today see the properties of DFT and compare it with that the properties of Fourier transform, set transform, etc. Okay, so we'll start with the presentation. Okay, so these are the properties of DFT. We have seen the different properties of Fourier transform, set transform, etc. So we shall see what are these properties. In the case of DFT, you know that signal, when you sample the signal in frequency domain, it's going to be periodic in time domain, and hence xn can be written as x in the angle bracket n with modulo n. That means if you have a series, say suppose n is um, capital N is 5, then your signal will be say from 0, 1, 2, 4. Suppose these are the first 5 samples. 1, 2, 1, 3. Okay, suppose these are the samples. Then this will get repeated. You will have the same 1, 2, 1, 3, 3, from 5, 6, 1 again, 7, 8, 9. So the 10 samples, you can see that whatever is from 0 to 4, it gets repeated from 5 to 9. So this gets repeated in all the way. So that's what is represented here. Xn is xn of modulo n. So if this is the condition for xn, the condition for DFT also is same. Mode xk is also periodic and discrete, and with the same period capital N. We will not be going to the proofs of this because we have seen elaborately what are the proofs of Fourier transform and set transform. These are applicable to this also. So you can refer this text for these proofs if you have any doubts. Probably one or two properties which are tougher we can solve in the class. Okay. Similar to that, you have circular shift x n minus m, a shift of m which is circular, which is notated by this modulo n in the frame of n samples. If you do the shift xn minus m n, it is going to be, suppose you have a signal x n minus m, then the set transform of this, if you have a signal x of n, set transform, suppose it is x of z, then the set transform of xn minus m will be xz z raised to minus m. all these things we have proved. So in a similar way, you can prove this also. You know that Z raised to minus m in the Z transform changes to W n raised to mk, where Wn is e raised to minus j2 pi by n. So similar to this, this change will happen here also. You will have xz into z raised, instead of z raised to minus m, you will be having Wn raised to minus j2 pi by n into mk, or Wn raised to minus mk. So this Wn is e raised to plus j2 pi by n. So you'll have Wn raised to minus mk here. So this is the Wn raised to minus mk into capital Xk, that is the DFT. Similarly, when you have a shift in DFT, that is a time domain shift, you can see that there is a shift here. If you have that shift, that will appear as Wn raised to mk. We know that in the Z transform also, if you have x z minus z0, it's going to become z0 into xn. So similar to that, this property is going to happen. So similarly, if you have circular convolution, this we already have seen. If xk and gk are going to be multiplied in frequency domain or in DFT domain, it's going to be circularly convolved in time domain. Capital Xk is the DFT of Xn, capital Gk is the DFT of Gn. In that case, if you multiply these two DFTs, circular convolution of Xn and Gn happens. While if this was normal Fourier transforms, if this Xk and Gk were normal Fourier transforms, they will, if you multiply them, it will be linear convolution. We know that. Now, time reversal. We know that time reversal in a frame of capital N is going to be in the DFT domain also. It is going to be the time reversal of DFT. And conjugate symmetry. This is one property we have not seen till now. So we shall see what this is. And Parseval's theorem is basically if Xn and Gn were same, this is going to be the energy of the signal Xn. So basically, signal of energy of the signal in time domain can be found as sigma Xn square, which is the same as sigma Xk square, or the sum of the squares of frequency domain. So you can find energy from either time domain or in frequency domain, both will be the same. So that's what Parseval's theorem tells. So let us see what is conjugate, complex conjugate or conjugate symmetry property. Okay, so this is conjugate symmetry property. We shall see what this conjugate symmetry property is. Okay, let us go back to a Fourier transform and solve it there, and let us come back and see what is happening in DFT domain. Okay, suppose you have x of t, it have a Fourier transform represented as x of j omega. This is continuous domain signal. X of t is continuous domain signal, and xj omega is its Fourier domain representation. This is xt can be assumed to be non-periodic, aperiodic, and hence the representation is Fourier transform. Now find the, okay, so what will be the Fourier transform of x of minus t? By applying the equation integral minus to infinity xt raised to minus j omega t, if you replace t with minus t, it is going to be x minus j omega. I'll just show it here. Integral minus to infinity xt e raised to minus j omega t. This is what x j omega is. So if you want to find the Fourier transform of x minus t, replace t with minus t. So integral minus into infinity x of minus t e raised to minus j omega t. This is what we want to find. Suppose you replace t with minus t or minus t with u, then this become xu e raised to n minus t become minus t. So this become minus of j omega minus u. Since t is minus u, du, you have minus sign here. So integral from minus to infinity. So this is going to become x of minus j omega. If you take this minus u to here omega, this become minus omega into u. So this is going to be integral minus to infinity xu e raised to minus j minus omega into u, which is x of minus j omega. So this is x of minus j omega. So x of minus t have a Fourier transform x of minus j omega. Now what happened if you take the Fourier transform of x of x star t, that is the complex conjugate of xt? Fourier transform of this, to find the Fourier transform of this, you integrate with respect to integral minus infinity to infinity x star t e raised to minus j omega t dt. This is what you want to find. And how will you find this? Integral, this is x j omega, or other way of doing this is you can write, okay, from this itself, you know this x j omega is integral minus to infinity xt e raised to minus j omega dt. You put a conjugate in both sides. So for this also you'll have a conjugate. So x star j omega is equal to integral minus to infinity xt, the complex conjugate, let us take it inside to the integral e raised to minus j omega t. You'll have a conjugate for this also. dt is real, so that don't have conjugate. So this you can write as integral minus to infinity x star t e raised to minus, what is the conjugate of e raised to minus j omega t? You know that e raised to minus j omega t, okay, j cos omega t, it will be cos omega t plus j sin omega t. E raised to minus j omega t is cos omega t minus j sin omega t, and its conjugate is cos omega t plus j sin omega t, which is e raised to j omega t. So this will become e raised to j omega t dt. This can be also written as minus j omega into minus j. You can take a minus outside, multiply with minus. So it becomes e raised to minus of minus j omega t dt. Okay. So what is this? What is the right hand side? It is the Fourier transform of x star t. So x star t has a Fourier transform x star j omega. So here you have a minus sign. If you take minus j omega to this side, or if you replace omega with some other variable, this become, or the Fourier transform become x star minus j omega. So x star t has a Fourier transform x star minus j omega. X star minus j omega. This property is called conjugate symmetry property, and if xt is real, suppose xt is real, if xt is real, what happened? xt is real, then x star t is going to be xt itself. X star t become xt itself. So xt will be having a Fourier transform of x star minus j omega. Okay. Okay, we shall continue next this. Okay. Before coming to this, oh, what happened if xt is okay? To this details we shall come later. Like what happened when xt is real and even, and what happened when xt is real and odd. So those things also we can analyze. It's pretty interesting to do that. But as of now, we shall come back and to the property of DFT. Yeah. So if you have x star t, your Fourier transform is going to be x star. If this was x star t, the Fourier transform was going to be x star minus j omega. Similar to that, in the DFT domain, if you have x star n, your DFT domain will be x star minus k mod n. Okay, and the Parseval's theorem. Okay. Now, yeah. How will you convolve two signals? One is a finite, you cannot call finite series. Finite is a finite supported signal. And another infinite series. That means suppose you have xn, say from 0, 1, 2, 4, and 3. This is one signal xn, and suppose, or let this be hn. Let us represent this as hn and this one as xn. This is hn. And suppose you have xn, another series, which is say an infinite series or a very large series. 1, 2, 4, 3, 1, 8, like that. 4, 5, 6 is going to infinity, or to a very large number m, or m minus 1. This is a m size series, or m is very large. In these cases, how will you efficiently find the convolution? Is there any easier method to find the convolution? That is the next question. So for that, we have two methods. I'll write these methods here. One is overlap add method. Second is overlap save method. Overlap save method. Let us see the first method, overlap add method. You have this hn and xn, and you want to convolve this. Basically, your problem is you want to convolve this easily. If you have xn, which is a very large series or infinite series, then time reversing it may not be efficient because the signal is somewhere. And when you have streaming data, convolving this may be difficult. So let us find some easier method or an efficient method for finding the convolution of xn and hn. Okay, suppose you have this xn And suppose you can split this, say like this. You split this into small blocks. Let this be one block, and you take another block, say from this, from here you have another block of 4. Then you take another block, say another block from here, which is 4 of length 4. Like that, you split this into small sequences, and let us call this x1n, and you call this x2, or let us call this as x0n, this as x1n, this as x2n, like that. So basically you know that xn is x0n plus x1n plus x2n, etc. If you add this together, it is going to be xn, and you have hn, which is a small sequence of size 4. So this is of size 4, this is of another size 4, all these are of size 4, this is also of size 4. Now you can, to convolve xn and hn, you can convolve x0n and this, convolve these two, you convolve these two, you convolve these two, and add them together. Then you get the output y of n. And for this, you can utilize circular convolution if you want. How do you do circular convolution? To do linear convolution, you know that you have two signals. Say you want to convolve x0n and h of n. If you want to do this convolution, what you can do is you find the size of this. Let this size be, we know that both are of size 4. Let us generalize this as size m. Okay. So if you linearly convolve this, it will be 4 plus of length. If you linearly convolve these two, it will be of length 4, length of this plus length of this minus 1. So 4 plus 4 minus 1, or 2 into 4 minus 1, 7 of length 7. So this is basically of length 4. So the remaining 3 points you can do 0 padding and do the you have a hn of size 4. In that also you do 0 padding with a length of 3. So now these two have length of 7, and if you do circular convolution with this, you are going to get the linear convolution. So you can proceed with the same thing. You can convolve hn, with linear convolution through circular convolution by 0 padding. So you do the through circular convolution, you do the linear convolution and add them. That is basically what you do in overlap add method. And in overlap save method, we'll go in detail into this. We'll do with example probably in next class. But I will just give an introduction to what these things are. And in overlap save method, what you do is, again, you have a very large series xn. You want to convolve with h of n. You will do 0 padding at the beginning of the signal, and you will do some linear convolution. And when you ignore some values and add them together, you will again get the output y of n. So these two methods are the methods used for finding the convolution of a finite support signal with an very large or infinite support signal. Um, so we'll go into detail and we'll do some problems from this in the um, next class. Okay. So this is the method. Okay. By the way, I'll just show you what happened when we'll come back to the conjugate symmetry property and see what happened when signal is real and odd, real and even, etc. We already saw that x star t has a Fourier transform x star minus j omega. We already know that x of minus t x of minus t has Fourier transform x of minus j omega. So if x of t, suppose x of t is real and even means x of minus t will be x of t itself. Even signal means x of minus t will be x of t itself, and odd signal means that x of minus t will be x minus of x of t. So this equation x star t is same as x of t because signal is real. So x of t also have a Fourier transform x star minus j omega. Similarly, x of minus t is same as x of t because x is even. So its Fourier transform is x of minus j omega. So if you see, you can see that x of t has Fourier transform x of j omega. It is you already know that x of t has a Fourier transform x of j omega. So these two are same. That means x of j omega is even. These two are same means x of j omega is even. And x of t has Fourier transform x star minus j omega. So x of t has a Fourier transform x of j omega. This is also true. You know that x of t has a Fourier transform x of j omega. And since x of j omega is even, x star minus j omega, or this you can write like this also. Both are same. X star, x j omega is even means x of minus j omega and x of j omega are same. So if you compare these two, x star minus j omega and x of minus j omega are same. That means x of j omega is real. So if xt is real and even, x of j omega is going to be real and even. We found that x of j omega is real and x of j omega is even. Similarly, suppose that you want to see what happens to x of t when x of t is say something else, real and odd. Suppose x of t is real and odd. In that case, again, conjugate symmetry property shows that x star t has a Fourier transform x star minus j omega. Xt is real means x star t is xt. So xt has again Fourier transform x star minus j omega. Similarly, xt is odd means you take x of minus t. X of minus t has a Fourier transform x of minus j omega. But x of minus t is minus x of t because xt is odd. So this is having a Fourier transform x of minus j omega, or x of t has a Fourier transform. You take the minus to this side, minus x of minus j omega. Now x of t, you know that x of t has a Fourier transform x of j omega, which is general Fourier transform of x of t. X of t has a Fourier transform x of j omega. Now if you compare these two, you can see that x of j omega, you take, if you compare this equation, suppose you call this 1 and 2, if you compare these two equations, you can see that x of minus j omega is same as minus x of j omega. That shows that x of j omega is odd, right? And what can you tell about, okay, so x star t is x star minus j omega. From, suppose you compare these two, xt as Fourier transform. Suppose you call this 3, x star minus j omega, 3 and 2, suppose you compare, x star minus j omega is same as minus 3 and 2. Compare 3 and 2. X star minus j omega is same as minus x of minus j omega. Or x star j omega is same as, you can minus and minus you can remove. So x star j omega is same as x minus of x of j omega. That means if you do conjugate of x j omega, what is happening is you get a negative sign. You have a number, if you are conjugating it, you get a negative, means it is purely imaginary, because if you have 3 plus 2j, the conjugate is 3 minus 2j. And suppose you have 5j, if you take conjugate, it become minus 5j. That is just a negative sign. It means that the signal x j omega is purely imaginary. So if xt is real and odd, capital X j omega is going to be real. Is it real? Sorry, it is purely imaginary. X j omega is purely imaginary. And odd also. So now what we understood is that xt, if it is real and even, x j omega will be real and even, while xt, if it is odd, sorry, if xt is real and odd, x j omega is going to become purely imaginary and odd. So this property, all these properties are applicable to DFTs also. So I just want to convey these things to you. So I think we shall stop now. It's almost 9:10. Okay, I'll stop recording.